Hello everyone. So for now, we're going to discuss Module 8, which is on MOSFETs or Metal Oxide Semiconductor Field Effect Transistors. So for this module, we'll have a brief introduction and then we'll discuss how the MOSFET operates, and then we will discuss the models that are used for the different modes of operation, and then this would be part 1, and then I will be recording another lecture or another video for part 2, which will be mainly discussing the analysis of MOSFET circuits. So as I mentioned last time, transistors, when we discussed BJTs, transistors are generally grouped into two types. So the bipolar transistors, which are the NPN and PNP, and then the field effect transistors, which can then be further categorized into junction field effect transistors and MOSFETs. Now, for this class, we're going to focus on MOSFETs, specifically enhancement type MOSFETs. So enhancement type MOSFETs are type of field effect transistors that are normally off, whereas depletion type would be normally on. So for EE123, we're going to focus on enhancement type, and we're going to focus on NMOS type of enhancement MOSFET. So there's an NMOS, that means an N-channel MOSFET, and there's also a PMOS counterpart to that, which will be presented to you in EE131 next semester. So to start off, we first look at the NMOS structure. So an NMOS is usually fabricated on a P-type substrate. So we have a P-type substrate here. And then there are regions in the substrate that are doped to make them N-type. Okay, this would then form the two terminals of the MOSFET or of the NMOS, as you will see later on. Now, after doping these regions, the next step is to deposit oxide. So this oxide in NMOS is usually silicon dioxide. After depositing the oxide, a metal is deposited on top of the oxide. So this region in the middle, wherein you have the metal, the oxide, and then the P-type semiconductor under it, that is actually the MOS or metal oxide semiconductor in the name MOSFET. Now, this metal is actually in modern NMOS devices, this metal is usually heavily doped polysilicon. Now, this is the structure of the NMOS, and it has three terminals, namely the source, the gate, and the drain regions, okay, as annotated on this slide here. So how do we then operate the NMOS? So first, you notice here, the source is connected to ground. The source terminal is connected to ground. And then we apply a voltage at the gate. So suppose we apply a voltage that is positive to the gate. Now remember, the P-type semiconductor, okay, the substrate, has more holes than electrons, so that when you apply a positive potential at the gate, the tendency for these holes is that they are pushed down to the substrate, to the bottom of the substrate, no, not on the surface. So that means, therefore, that what happens is the holes, okay, near the surface of the oxide and semiconductor interface are then filled up by electrons, as is shown here. So when you imagine holes being pushed down to the substrate, then that means those holes are being filled up by electrons. Now this region under the oxide of electrons here, that is what we call the inversion layer or the channel. So the application of a vertical field via a positive gate voltage allows the formation of the channel under the oxide. Now at this point, there's still no conduction going on, because what you ultimately need for conduction to happen, for current to flow, is you need to apply a lateral or horizontal field in the form of a positive voltage at the drain. So when you apply a positive voltage at the drain, note that now you have an N-type drain, an N-type channel because of the electrons at the surface, and then an N-type source. So by applying a positive voltage at the drain, that actually attracts the electrons so that electrons would flow from the source to the drain. Okay. Now, if electrons are flowing from the source to the drain, because we define positive current as the flow of positive charges, then current flow would be from drain to source, as is indicated here. So that is basically how the NMOS operates. You need to apply a positive gate voltage to form the channel under the oxide, and then once you have the channel, you need to apply a positive drain voltage to allow the flow of electrons from the source terminal to the drain terminal, resulting in current flowing from the drain to the source. So to summarize, okay, the metal oxide semiconductor field effect transistor, specifically the N-type MOSFET, which is the NMOS, has three terminals. So we have the gate, which is insulated from the substrate. So we apply a vertical field at the gate, and this would result in the formation of a channel under the oxide or the insulating material. And then the source terminal would be the source of carriers that crosses the channel when a lateral electric field is applied via a voltage at the drain, as was explained previously. And then the drain is the destination of the carriers that crosses the channel, again, when that lateral field is applied. Now, the gate voltage that is needed to form that channel is actually what we call the threshold voltage. When the gate voltage is equal to the threshold voltage, that means that the concentration of electrons under the gate oxide is equal to the concentration of holes of the substrate. So the initially p-type substrate region is inverted into an N-type via this threshold voltage. So that means that for NMOS, when VGS is equal to the threshold voltage, that means enough electrons would have been attracted to the oxide semiconductor interface to create a path for current to flow. So you can imagine it. Okay, why did we say VGS equal to VTH? Remember, okay, in our illustration a while ago, we actually connected the source terminal to ground. So we define the threshold voltage as being referred to the source terminal. So when your VGS is greater than or equal to the threshold voltage, then you form the channel, the N-type channel, under the oxide. Okay, so that's the side view of the NMOS. Okay, when we look at it from the physical structure point of view, and you could actually think or compare this with your NPN, right? So that for the NPN, the structure is you have a vertical transistor. Okay, the flow of current is vertical, but for the MOSFET, it's horizontal, and you need to apply two voltages to make that happen. Now, the schematic symbol of the NMOS is shown on the left here. So we have the gate on the left, so that's synonymous to the base terminal in BJTs, and then the drain at the top, and then the one with the arrow is the source terminal. So it's annotated here that we have your VGS, which is the voltage across the gate and source, and VTS, which is the voltage across the drain and source. Now, because of the way that the NMOS is structured, where you have an oxide under the metal, so the substrate is actually insulated from the gate terminal so that the gate current in all regions of operation would be equal to 0. Since the gate current is 0, that means therefore that the drain current should be equal to the source current. So we usually just use ID. And that means that when ID is of a certain value, then correspondingly IS would be a certain value. Note that if ID is entering the transistor, IS should be leaving or directed away from the transistor. Now, there are three regions of operation for the NMOS. The first one is the cutoff region. So the cutoff region the happens, or the NMOS is in the cutoff region when the gate to source voltage VGS is less than the threshold voltage. At this point, ID is equal to 0, and so therefore the transistor acts as like an open circuit. The third region is in saturation. So at this region, your VGS is greater than or equal to VTH, and your VDS is greater than or equal to VGS minus VTH. So at this region, you actually have drain current that varies squarely with VGS. You see, as you can see in the equation, there's a K times VGS minus VTH quantity squared, 1 plus lambda VDS. So this equation tells us that the drain current varies with VGS as well as with VDS. But in saturation, okay, typically, especially in discrete NMOS devices, lambda is very close to 0. So lambda here is a coefficient that factors in some non-idealities in the MOSFET. And for triple E123, we're just going to consider, at least for now, ignore the effect of VDS on ID when the transistor is in saturation. So we're going to simplify the equation into ID equal to K times VGS minus VTH squared. Now, if we're going to compare these regions of operation with the BJT, the cutoff region is synonymous to the cutoff region in BJT. The linear region here is actually the one that's synonymous with the saturation region in BJTs, because the linear region here is when you have small VDS or output voltage. Diba sa saturation sa BJT, yung saturation doon, yun naman yung VCE yung small. Okay, because in BJT, when you say saturation region, ang nagsasaturate would be voltage. Whereas in MOSFET, when we say saturation, what saturates is the drain current. Because when VDS is high, okay, the drain current tends to be constant or changes very slowly because lambda again is very close to 0. Okay? So, yung saturation region sa MOSFET, yan yung analogous sa forward active sa BJT. Okay, keep that in mind. Okay, now, if we're going to analyze the equation, so kung yung NMOS in saturation yung synonymous sa BJTs in forward active, ito yung ating operating region of interest if we're going to design amplifiers. So in NMOS in saturation, our equation for ID is K times VGS minus VTH squared. So if we're going to plot that, okay, this equation is only valid when VGS is greater than VTH. Okay, kasi pag less than VTH, alam natin ang ID should be 0. So if you look here in this plot, when VGS is less than VTH, ID is 0. And then when VGS is greater than VTH, that's when you have the square or the parabolic curve, okay, relating ID to VGS. So this region where VGS is less than VTH is again the cutoff region, and that region where you have the parabola is the saturation region. Now, to identify in a characteristic curve of the MOSFET, to identify when the linear region and the saturation region happens, we have to look at the ID versus VDS curve. Okay, so this is the one that's synonymous to the IC versus VCE curve in BJTs. So in this plot, shown here is the drain current with respect to VDS for increasing VGS value. So VGS4 is greater than VGS3, is greater than VGS2, is greater than VGS1. Now, this region here, where VGS is still less than VTH, so that the drain current is effectively zero, is the cutoff region for this plot here. Now, between linear and saturation, we said that ang conditions natin is VGS should be greater than VTH, as well as there's also a condition for VDS. Yung boundaries natin would be when VDS is equal to VGS1 minus VTH. So, if you notice here, as VGS changes, nagbabago yung boundary na yon. Unlike in BJTs, na ang boundary lang natin is VCE SAT na 0.2 constant. Here, for MOSFETs, let's say if you have VGS1, ito yung VGS1 minus VTH. Okay, you can look at it at sa x-axis. Sa VGS4, nag-move yung ating VGS4 minus VTH. So that yung saturation region natin, yung pink dito, you could see, depending on what VGS we are operating in, nag-iiba yung range of VDS kung kailan saturation yung MOSFET. So, ito yung region na saturation. So, to complete our analysis, ito yung linear region. Okay? Yun yung mga regions wherein VDS is less than VGS minus VTH. Okay, so these are the characteristics of the MOSFET. If you'll notice in saturation here, hindi nagbabago, at least in an ideal MOSFET, hindi nagbabago yung IDS with respect to VDS. So now that we have looked at the operation of the MOSFET, we could actually now say na, okay, depende pala sa region ng operation, kaya nating i-model yung MOSFET. So, sa cutoff, zero yung current. Sa linear region dito, makita natin, lalo na pag masyadong maliit yung VDS, para siyang resistor. Kasi, meron ka lang line relating the current to the voltage, and that line crosses the origin. Whereas in saturation, it's as if meron kang constant current. Okay? Therefore, if that's the case, then we have the following models for the different regions of operation. So, for MOSFETs, in cutoff, we just model it as an open circuit. So, ganito, open lang, walang connections yung gate, the source, the drain. And then, in this region, the drain current is zero. And to check na tama yung assumption mo, if you're, let's say, if you're going to assume na cut off yung MOSFET, so you set the drain current to zero, dapat ang makukuha mong VGS should be less than the threshold voltage. Now, for a MOSFET in the linear region, as I mentioned kanina, we model it as a resistor across the drain to source. So, bakit open yung gate to source dito? Dahil nga, may oxide tayo sa gate. So, open circuit talaga from the gate dahil yung gate current natin palaging zero. Now, para malaman yung resistor na yan, kung ano yung value, we note that we have an equation for the drain current in the linear region. So, we just get the derivative of that with respect to VDS. Okay? And yung reciprocal. Kasi yung derivative ng ID with respect to VDS, that actually gives us a conductance term. Okay? So, pag kinuha natin yung conductance term, yung derivative with respect to VDS, ang makukuha natin would be, kasi may VDS tayo sa labas, so matitira dito is VGS minus VTH, tapos yung VDS over 2, ang derivative niyan, kasi magiging VDS squared over 2, so magiging 2 VDS over 2, kaya magiging minus VDS na lang. Okay, so you can just try getting the derivative of this part here. And then the reciprocal of that would be 1 over 2k VGS minus VTH minus VDS. Now, at least for EEE1E, we will only consider the cases wherein VDS would be usually small din naman at the linear region, so that we could say that for MOSFETs operating in the linear region, for our case, VDS is very small, so that we could approximate RDS on as just 1 over 2k VGS minus VTH. Okay, we want to use this approximation because this means we only need to determine what VGS is, and then we'll be able to use that to approximate the resistance if the MOSFET is operating in the linear region. Now, for saturation, as I mentioned din kanina, we just model it as a current source, and the current source has a value in saturation na K times VGS minus VTH squared. So once you already have a value for VGS, you just plug it in this equation here, and then that's the value of the current source, and that current source would have a certain voltage VDS across it. Okay, so para i-check kung saturation nga siya, kailangan ma-check mo na yung VDS na yon is greater than VGS minus VTH. Now, how does amplification happen when we have a MOSFET in saturation? So note that what we have here on the left is the drain current versus VGS. So ito yung pinakita natin kanina. So these are curves for ZVN3306A NMOS. The green plot is the model. So that's our equation na K times VGS minus VTH squared. And the blue dashed plot is the actual characteristics as measured for this device. So what you see here, very close naman yung ating model. And you could easily identify no, na kung nasa yung threshold voltage is somewhere below 2 volts. And then after the threshold voltage, then you have this saturation mode of operation. Now, if we look at this plot, and if you consider the case, for example, okay, we're looking at around 5 volts na VGS. Okay, pag nagbago yung VGS ng maliit lang, konti lang, magkakaroon ka ng konting change sa current in the range of around 0.4 amperes, right? So, around 0.4 amperes, tas pag tinignan natin yun sa ID versus VDS curve, yung 0.4 amperes is somewhere here, right? Yung pag-change ng current around 0.4 amperes by a small amount for that VGS value would actually mean or represent a corresponding change in VDS that is large. No, pag tingnan natin yung x-axis, VDS here changes from around 3 to 10 volts. So a small change in VGS, which is our input voltage, would result in a large change in VDS, which is our output voltage. So that's how we have voltage amplification when we're operating in saturation. Okay, so that actually ends part 1 of module 8. So next we'll have part 2, which is more on circuit analysis for MOSFETs. So for this lecture, make sure that before going into part 2, make sure that you understand how the MOSFET operates and how they are modeled. Okay, dun sa tatlong regions of operation niya. Again, I hope that once you finish this, if you have any questions, do not hesitate to post questions in Oble or send me an email. Okay? Okay, stay safe everyone.